Good afternoon, everybody. And on behalf of the Indian Economic Review, it's a pleasure to welcome you all on a fairly hot and sultry afternoon. What I'd like to do is to actually say a little bit about the journal, the Indian Economic Review, since there are many of you who have probably not from Delhi School, or even if you are from Delhi School, maybe you haven't read the journal. And this introduction was supposed to have been done by Professor Pami Dua, who is the director of the Delhi School. But unfortunately, she had another commitment and couldn't be here. So on her behalf, I'm going to request Abhijit Banerjee, who is one of the associate editors of the journal, to come and speak on her behalf.
Hi. Okay, so welcome. Pardon me for reading, but I'm just reading out Pami's message. She welcomes us all, and she's made a couple of, or 2 or 3 specific observations about the Indian Economic Review, which I'd like to share. So I'll just start reading out now. The Indian Economic Review, the journal of the Delhi School of Economics, was founded in 1952 by the founder director of the Delhi School of Economics, Professor V.K.R.V. Rao. Since then, the journal has been ably stewarded by several faculty members over the years, including Professors K.N. Raj, Manmohan Singh, Prashanto Pattanayak, Dharma Kumar, V.N. Pandit, Partha Sen, and Pami Dua herself. As a result of their efforts and those of the current editorial team, the Indian Economic Review acquired a reputation for featuring high-quality papers in all areas of applied and theoretical economics. It has been privileged to feature the work of Nobel laureates, including that of Jan Tinbergen, James Tobin, James Mirrlees, George Akerlof, and William Nordhaus. Nordhaus also happens to be a co-author of our distinguished speaker, Professor Maureen. For nearly 6 decades, the journal was run as an in-house publication. Since 2017, it is being published by Springer. The journal is scaling new heights and is now indexed in Scopus. In recent years, downloads of some of the journal's papers run into tens of thousands, and its recently introduced policy review section, which aims to bridge the gap between academics and practice, has been particularly successful. A long-held tradition at the Indian Economic Review was its annual public lecture by an eminent economist on a topic of broad interest and importance. After a considerable gap, the journal was able to revive this tradition last year, with Melissa Dell speaking on persistence and transformation in economic development. This year, we are very fortunate to have Professor Maureen Cropper deliver the annual public lecture.
Thanks. So I'd like to now invite the editor-in-chief of the Indian Economic Review, Uday Bhanu Sinha, to come and introduce the speaker.
Good afternoon. I am Uday Bhanu Sinha, professor at the Delhi School of Economics and editor-in-chief of the Indian Economic Review. IER is delighted and honored to host Professor Maureen Cropper for its annual public lecture. I have the difficult task to summarize in a few minutes her contributions to economics in a long and distinguished career spanning 5 decades. Professor Cropper completed her undergraduate studies at the prestigious Bryn Mawr College, where she graduated with the highest academic distinction possible. She went on to get a PhD in economics from Cornell University in 1973. Professor Cropper is among the world's leading environmental and resource economists. She has worked on an incredibly large range of topics, ranging from environmental valuation to deforestation, air pollution, and climate change. For the last 3 decades, her research has focused on
Oh.
developing countries, especially India.
Maybe not, yeah, okay.
One theme that has
Yeah.
dominated her work is air pollution, on which she will be speaking this afternoon. There are 3 aspects that distinguish Professor Cropper as an economist and as a person. First is her willingness to engage in issues of immediate practical concern, such as human health. Her work is unique combination of academic rigor along with the ability to get into the nitty-gritty of real-world data. It is also remarkable for her openness to work with experts from other disciplines, such as epidemiologists, air quality modelers, transport experts, and many more. Second, Professor Cropper is a teacher and mentor par excellence. She is well known for being generous with her time, advice, and support to all her students, be it undergraduate, masters, or doctoral students. She has supervised generations of PhD students, many of whom have gone on to become leading economists in their own right. I may note here her particular affinity for students from India, where she has guided more than a dozen PhDs. She is indeed a role model as an academic mentor and teacher. Third, as a leading female economist, Professor Cropper has broken several glass ceilings. She was the first female president of the Association of Environmental and Resource Economists and the first female chair of the Department of Economics at the University of Maryland. In addition, she has headed key committees at the National Research Council and the US Environmental Protection Agency. In a male-dominated profession, Professor Cropper has been a trailblazer and inspiration for women. Academic and professional accolades have accrued to Professor Cropper in plenty. To name just 2 of these, she was elected to the prestigious US National Academy of Sciences in 2008 and is on the board of directors of the National Bureau of Economic Research. Please join me in welcoming Professor Maureen Cropper.
I think so now. Okay.
So before I invite Professor Cropper to speak, just a couple of housekeeping things. We'll have a question and answer session after she speaks. And at this point, even if there are questions that are somewhat clarificatory, I'd advise you to hold on to them until she's done with her talk, because most likely she would have addressed any questions that you may have had. And before I get off the stage, I just want to do a sound check. If you could just speak into your headset and make sure that people at the back can hear you.
Can everyone hear me in the back? Yes, sounds good. Okay, well, thank you. Yes. Okay, well, first of all, let me say how honored I am to be asked to give the annual IER public lecture. I really am happy to be here. I am happy to talk about the health benefits of air pollution control in India. But again, to succeed Melissa Dell, who is a fantastic economist, I really feel honored to be here, and I hope I will not disappoint. I guess I can put my water there. Okay, so I'm going to be talking about the health benefits of air pollution control in India. And I've added a co-author to my paper, Youngjun Park. Youngjun was a graduate student at the University of Maryland. He's now an assistant professor at the University of Massachusetts Amherst. And I'd like to think that in part, I have actually, sorry, someone's waving, that I have actually converted him in part, at least, from being an industrial organization economist to an environmental economist. But he's responsible for a lot of what you're going to see today. Okay, so I'm going to focus on 5 questions about air pollution in India. The first question is, how high is ambient air pollution in different parts of India? When I talk about air pollution, I'm going to mean fine particles, ambient, no, sorry, not just ambient, but fine particles, PM 2.5. So particles less than 2.5 microns in diameter, and capable of penetrating the lung deeply. So PM 2.5 is what you can think about. There are actually two major sources of exposure to PM 2.5. The first is outdoor air, ambient air, but there's also indoor air pollution. For people in many states of India, they are actually receiving a higher dose of PM 2.5 fine particles from indoor air pollution, from burning solid fuels for cooking and sometimes for heating, than they're getting from the outdoor air. What we're going to look at is the morbidity and mortality consequences of both outdoor air pollution and indoor air pollution. We'll also see that indoor air pollution is an important contributor to what people are breathing outdoors. We'll move on to talk about the health costs of pollution-related morbidity and mortality. And this is, I'm going to focus there on the loss in output when people are sick or when they die prematurely. If you're interested in controlling air pollution, it's very important to look at source receptor results to see exactly what the sources of ambient air pollution are in different parts of India and how air pollution travels across borders. So we'll spend a little time on that. And I'll end up the talk describing work that I have done for many years with Sharath Garakunda and Pooja Jawahar of Urban Emissions Info. We have done, I think, about 5 papers looking at the health benefits and costs of reducing pollution from coal-fired power plants. So that is the general plan of the talk, and I want to make sure, see what time it is so I don't go over more of my allotted time. Okay, so let me start by talking about air pollution levels in India. So there are 3 methods that can be used to measure ambient air pollution. The first is ground-based monitors. The Central Pollution Control Board has over 800 monitoring stations in India. It's important to look at what's happening on the ground, both for fine particles and also other common air pollutants. Problem is, you may be looking at parts of the country where there aren't monitoring stations, or you may want to analyze a policy, a counterfactual policy, where you've got to estimate the impact of the counterfactual policy. So it's necessary to model ambient air pollution. And the second method here is to use modeled estimates from atmospheric chemistry models. This requires an emissions inventory, and it requires meteorological data. Examples of this approach are Urban Emissions Info work, but also work by IASA in Vienna, which has developed the Gaines model. And we'll also see some results from the Gaines model, as well as results from Sharath and Pooja. The third way to measure ambient air pollution is to use satellite data, to use information on aerosol optical depth, to combine it with atmospheric chemistry modeling. And that's the approach the Global Burden of Disease has used. We'll look at some of those results. Shagnik Day at IIT Delhi also produces estimates using satellite data. And of course, if you're going to model ambient air pollution, you've got to compare your results with what's going on the ground. So what you're seeing here is modeled estimates of average annual PM 2.5 in 2018 from IASA's Gaines model. If you look at the bar on the right-hand side, areas that are more orange, red, or actually brown are areas with higher levels of ambient annual PM 2.5. As you can see, in the Indo-Gangetic Plain, you have areas where annual average PM 2.5 has been estimated to be over 90 micrograms per cubic meter. That's an annual average. This includes Delhi. If you look at other areas, I suppose I really should try to use the pointer, but I was told to stay here in front of the podium, so it's a little bit of a trade-off. but so I maybe should stay here. If you look at the colors in Rajasthan and Gujarat, they're orange. So we're talking about areas where there are perhaps like 60 micrograms per cubic meter annual average. And also in the eastern part of India, where there are many power plants. But as you go down to the south of India, you're seeing much lower ambient concentrations on the order of 30 micrograms per cubic meter. Not, exactly totally the lowest you might imagine, but certainly much lower areas. When you look at the results that come out of the global burden of disease analysis, the broad picture is really quite similar. These are estimates for the year 2019. And if you take a look at the map on the left-hand side of the screen, let me just see how the colors turned out here on the screen. Okay, they're not terrible. What you're seeing when you look at the states of when you look at Delhi, but Uttar Pradesh, Bihar, Haryana, these are states in red, indicating that the modeled estimates from the GBD suggests annual ambient concentrations greater than 100 micrograms per cubic meter. In Rajasthan, in Jharkhand, in Punjab, you're looking at levels between 100 and 80 micrograms. So these don't match up totally with the levels in the previous map, but their correlation is actually quite high. You're seeing really large levels in the Indo-Gangetic Plain, slightly lower levels in Madhya Pradesh, West Bengal. And then as you go towards the south of India, when you look at Karnataka, Tamil Nadu, you're looking at levels, 30 micrograms or less. By the way, I assume these slides will be made available, so things you can't see in detail during the talk, you can look at afterwards at your leisure. What the map on the right is showing is actually the percentage of households that are burning solid fuels in each state. So again, it's a little hard to distinguish, I guess, here, the very red states, which have levels in excess of 70% of households burning solid fuels, which are Odisha, Jharkhand, Chhattisgarh, Bihar, Assam also, and levels between 60 and 70% of households burning solid fuels are Rajasthan, Madhya Pradesh, Uttar Pradesh, and well, we can stick with those. So again, the colors are perhaps not all the one we want, but you certainly can distinguish at least the dark states, which are ones where you have significant percentage of households burning solid fuels, versus what you see in the south of India, where the percentages are much lower. This is going to be important when we talk about controlling air pollution, ambient air pollution in the Indo-Gangetic Plain, because we'll see that in that area, household air pollution is a big source of ambient air pollution. Okay, so I'm going to move on to, sorry, with a little water here, the health impacts of ambient and household air pollution. These are calculations that Yang Jun and I have made based on the estimates of exposure that you saw, at least for ambient air pollution, in the map based on the Gaines model. Okay, so what we have done in the results you're seeing are to use the methodology that the Global Burden of Disease used in its 2019 report to calculate the impacts of PM 2.5 in 2018. We're calculating impacts for grid squares of 1/10 of a degree by 1/10 of a degree, so roughly 11 kilometers by 11 kilometers. And we're calculating the impacts for 6 diseases: for ischemic heart disease, stroke, lower respiratory infection, chronic obstructive pulmonary disease, type 2 diabetes, and lung cancer. Okay, So the important thing to note is when you're calculating the health impacts of PM 2.5, your risk of dying of any of these diseases really depends on all the sources of PM 2.5 that you're exposed to, both outdoor and indoor. So what we do is to estimate for each of those grid squares, the population exposure to both sources, indoor and outdoor air pollution. And we calculate the fraction of deaths attributable to total PM 2.5 exposure. Then we allocate them to ambient, excuse me, versus household deaths by looking, in the case of ambient deaths, at total deaths that are attributable to PM 2.5 in the square times the fraction of total PM 2.5 that is due to ambient sources. Same for half deaths. Okay, so an important fact is that the health risks of PM 2.5 per microgram decrease as exposure increases. The concentration response function, which you'll see a picture of in the next slide, is concave. So what this means is that if you're controlling outdoor ambient air pollution, the impact of a reduction in a microgram of ambient exposure is going to be lower if people are already being exposed to household air pollution. If two areas, as the last bullet says, have the same ambient PM 2.5 levels, the one with the higher HAP exposure will have a lower death rate due to ambient PM 2.5. This has implications for pollution control, and this slide here is showing you a concentration response function for ischemic heart disease for people between the ages of 70 to 75. The vertical axis is the relative risk of dying from IHD given PM exposure, and the horizontal axis is your annual average exposure to PM 2.5 from all sources. So, as the slide says, the impact of inhaling an additional microgram of PM 2.5 declines the higher your level of annual average PM 2.5. Okay, why would this be? You know, the short answer might be, well, if it didn't decline, you would be attributing huge percentage of deaths to air pollution, to PM 2.5. There's also evidence from information on active smoking that impacts indeed do become less in marginal terms as smoking increases. And so one of the implications of this, which we'll see in the results, as the second bullet says, is that when you are reducing ambient air pollution, the marginal benefits from this are going to be smaller if people are already beginning with, say, 100 micrograms per cubic meter of exposure to household air pollution. The slope of the curve at 100 micrograms, if we start reducing from that point, is going to be lower than if we were starting from a lower total exposure. Okay, so what you're going to see in maps in the next couple of slides are our estimates for 2018 for ambient air pollution, deaths equaling over, or estimated to be over 740,000. And in terms of where these deaths are occurring, many of them are in the Indo-Gangetic Plain. There are significant numbers in Gujarat and Maharashtra. These, of course, also reflect total population because these are the estimates of total deaths in these states. What you're going to see is exactly where these deaths are estimated to occur on the next map. And then we'll control for population and we'll actually look at the death rate due to ambient PM 2.5. Okay, so what you're seeing in this map, again, I hope this comes across not too badly. The colors aren't as great as they are on my screen, I'm afraid. But what you're seeing are the number of deaths per 11 kilometer by 11 kilometer grid square. And other things equal, you're getting more deaths in areas with higher ambient PM 2.5. So you have concentrations of deaths in the Indo-Gangetic Plain, especially in Uttar Pradesh and Bihar, also in West Bengal. And you're also getting more deaths in more densely populated areas, which is why you also have a lot of deaths on the Indo-Gangetic Plain. In terms of, again, the colors here, I'm afraid, are not the greatest, but the fact that even though ambient levels are low in Tamil Nadu, you still have the green areas or areas where there aren't a lot of deaths. You really actually have considerable number of deaths per square when you get down to Tamil Nadu, and that is reflecting partly the fact that you don't have a lot of household burning of solid fuels there. So the impact of the ambient PM 2.5, even though the levels here are lower than they are up in the Indo-Gangetic Plain, they're still having significant impacts on deaths. When you do control for population, so you're looking at death rates, and once again, I hope this comes across okay, you see that the death rate, okay, is actually higher in Punjab and Haryana, areas where you have a lot of PM 2.5, but you don't have such a high percentage of households burning solid fuels as you do in Uttar Pradesh and Bihar. So when you look at the death rate, you've controlled for population, the impact of this interaction between household air pollution and ambient air pollution, I think, becomes clear. You also have much higher death rates in the central part of India, because in Gujarat and Maharashtra, you really don't have, in Telangana, you don't have such high burning of indoor solid fuels for indoor cooking. Okay, if we ask what is going on in terms of your direct exposure to household air pollution, the estimated number of deaths due to household exposure is over 600,000, over 660,000. Again, this is representing the direct exposure from cooking within the household. And interestingly, or unfortunately, if you look at the third bullet, in 8 states in North and Central India, conditional on being exposed, people's exposure is in excess of 90 micrograms per cubic meter. Okay, it's really high for those people who are exposed directly to household air pollution. In 18 states in India, when you look at the bottom bullet, exposure to household air pollution accounts for greater exposure than what you're getting from the outdoor air. So this is clearly an important problem in its own right. It's going to have implications for control of ambient air pollution. Once again, we have maps. I hope you will look at the slides because things seem to have come out better on the screen. But when you're looking again at the death per grid cell, per 11 kilometer by 11 kilometer grid cell, you're getting deaths in areas where you have a high percentage of households burning solid fuels. So you have deaths occurring again in the Indo-Gangetic Plain. In terms of the states that have the highest number of deaths from household air pollution, they are, as listed on the slide, Uttar Pradesh, Bihar, West Bengal, Rajasthan, and Madhya Pradesh. And finally, if we actually do control for population, if we look at death rates due to HAP in each grid square, the areas where you have the highest death rates, which are in Jharkhand, in Madhya Pradesh, in Chhattisgarh, in Odisha, these are areas where over half of people's PM 2.5 is actually coming from household air pollution. So before we talk about the costs of this, the lost output due to both ambient and household air pollution, if you look at the 7 states / union territories on the slide here, if you look at Punjab, Haryana, Delhi, Uttar Pradesh, Bihar, Jharkhand, and West Bengal, those 7 states are accounting for almost half of the ambient air pollution deaths in 2018 in India. They're also accounting for about half of the household air pollution deaths. Excuse me. The fumes, the emissions from household air pollution are also accounting for a large fraction of ambient pollution in these states. So 34% in Bihar and West Bengal, 21% in Delhi, Uttar Pradesh, Jharkhand, and 15% in Haryana and Punjab. So in terms of where to put efforts, this sends a message. The last couple of bullets on the slide state, and these are based on our calculations, if you reduce household air pollution, you get the double dividend of reducing ambient air pollution. So if you reduced ambient air pollution from current levels, which are very high in these 7 states, to 35 micrograms per cubic meter, which used to be the WHO standard, interim standard, if you cut in half the percentage of households that are burning solid fuels for cooking, you'd eliminate 160,000 deaths in these 7 states. If you reduced ambient air pollution to 10 micrograms per cubic meter, and you cut in half the percentage of households burning solid fuels, you'd eliminate almost 300,000 deaths in these 7 states. So the point here, I think, is clear in terms of the interaction between the 2 sources of air pollution. What we're going to look at next is actually, what are the economic costs of this? The results that I'm going to show you here come from an article in the Lancet Planetary Health, which came out in 2021, written by, and I have to read it off, sorry, the India State Level Disease Burden Initiative Air Pollution Collaborators, which is a mouthful, which includes Shrikant and myself and 141 other people. As I say, you can get more details by looking at the article in Lancet Planetary Health. So if we say, what are the health costs of PM 2.5? We could look at the direct costs of illness, the costs of medical treatment, but we could also look at the indirect health costs, which is the output that's lost when somebody is ill, or if they die prematurely, it's what the expected value of what they would have produced had they lived longer. So for those not familiar with the term, morbidity is measured in the global burden of disease by years lived with disability, YLDs. So if you're living a year with chronic bronchitis, then that's equivalent to a fraction of a year with disability. We valued the YLDs using lost output per worker in 2019, and we valued premature mortality in 2019 by looking at the present value of lost output. Oh, sorry, we missed a slide. So the bottom line on these results is if we aggregated these losses across all states in India, the loss attributable to air pollution in 2019, this is both indoor and outdoor air pollution, we estimated to be almost $37 billion, 1.36% of GDP. About 1% of that is representing the lost output due to premature deaths. and 8 billion of it, about 0.3%, is representing the output loss due to YLDs. There were estimated to be over 5.5 million YLDs in India associated with air pollution, both indoor and outdoor, in the year 2019. What I'm going to emphasize here is how these losses as a percentage of gross state domestic product varied by state. So the highest in terms of percentage loss is in Uttar Pradesh, with over 2% of GSDP being estimated to be lost due to both indoor and outdoor air pollution. 2% of GSDP in Bihar, 1% in Maharashtra and Tamil Nadu, and in Sikkim, less than 1%. You would expect, and that's what happened, is that the losses reflect very high levels of exposure to both ambient and household air pollution. What I'm going to do is to skip over the methodological slides, because it's probably not a good idea to present them at 3:30 in the afternoon, but they're in the slides. And so if you would like to read these to see how we did the calculations, indeed, you can look at the slides. But just to emphasize once again, the states where these losses as a percentage of GSDP were highest are the states in red. You see if they look red here. They do, okay, but they're also listed on the slide. Uttar Pradesh, Bihar, Rajasthan, Madhya Pradesh, and Chhattisgarh. The states with small losses are places that are relatively clean and where many households do not burn solid fuels. So Sikkim, Goa, and so forth. Okay, to emphasize the role that household air pollution plays in output losses, what I've shown on this slide are blue bars. I hope the colors are okay. Okay, the blue bars are showing the percentage of state GSDP attributable to outdoor air pollution. The orange bars, the percentage of state GSDP attributable to indoor air pollution. I hope you can read the names of the states underneath here. But what you can see, so you have to add the two bars together to get the total percent of GSDP that's due to that's due to, to PM 2.5. So the states, which we looked at in red before, Bihar, Uttar Pradesh, Madhya Pradesh, Chhattisgarh, Rajasthan, in 4 of those states, half or more of the losses are due to household air pollution. If you look at other states that have high losses, but it's due primarily to outdoor air pollution, they include Punjab, Uttarakhand, Gujarat, Haryana, Delhi. Okay, ambient ozone pollution also made it onto the slide. We won't talk about ambient ozone pollution today. The losses are also small. Okay, so to sum up these results on health costs, the losses from YLDs and premature mortality in 2019 are high. As I said before, in the aggregate, the morbidity losses are about 0.3% of GDP for the country. Morbidity losses a little over 1%. As we saw in 8 states, the losses are in excess of 1.5%. And for the country as a whole, household air pollution is accounting for about 36% of these economic losses. The comment here on the bottom that economic losses from air pollution far exceed what we've quantified. We are not looking at direct costs of illness. We're not looking at impacts of PM on agriculture or on ecosystems. These really are, I think, conservatively estimated impacts on lost output. Okay, so let's talk a little bit about sources of ambient air pollution and what they imply for pollution control. We're focusing on ambient because sources of household air pollution, I think, are clear, and the government has been trying to do something about them for many years. But when we look at ambient pollution, you know, there are many different sources. Once again, I hope the colors came out okay. These are source receptor results based on the Gaines model. And the legend on the right-hand side has a logarithmic scale. So when you look at power plants and their impact on ambient PM 2.5, the color, which at least on my screen looks like orange, is actually something that is between 3.16 and 10 micrograms. Okay. In areas where you see this sort of yellowish color, for example, when you're looking at the impact of large industries on ambient PM 2.5, that's between 1 and 3.16 micrograms. Okay. Colors that are blue and green are lower contributions. Okay, so you're seeing actually that ambient concentrations from power plants have a significant impact. There's an especially large impact in the eastern part of India, in Chhattisgarh and Jharkhand, in states where there are a lot of power plants. There are impacts of large industries. Again, you can see geographically how those are dispersed. Mobile sources are especially important in the Indo-Gangetic Plain, especially in Delhi and Haryana. And we'll look briefly, at least, and again, you can look at these in your copies of the slides, at the impacts of other sources. So the important thing here is that these impacts really do vary significantly geographically. In the lower left-hand corner, what you're seeing actually is the impact of household air pollution, it says residential and commercial burning, on ambient air pollution. And I will just, highlight the rest of these. The important thing is to understand, depending on where you are attempting to control ambient pollution, what the main sources really are. We'll look at this in detail for the 7 states we looked at a few minutes ago. But once again, you can look at the details when you look at the slides themselves. Okay, so here we are going back to the 7 states that account for half of the ambient and household air pollution deaths in 2018. Once again, it's hard to see the colors, I'm afraid, but going from left to right, the first source is burning of waste, municipal waste. The second is transport, which is the largest single source in Delhi, but also important in Punjab and Haryana. The next source is small industries. The next one, again, which is, I'm sorry, the colors don't come out very well on the screen. The next source here is household air pollution, residential and commercial burning. That is followed by the impact of power plants, that's what's in black, followed by natural sources. Large industries are blue. And the last 2 bars are representing emissions from agriculture, which, as you might suspect, are important sources of outdoor air pollution in Haryana and Punjab. Okay, so the point here, again, is that it's important to understand what you are controlling, what sector you need to control. For completeness, I also did bar graphs here for Bihar, West Bengal, Jharkhand, where is supposed to be the orange color here is, which is household air pollution, is really important in these states. Okay, so there are 2 take-home messages from this slide and the next one And I know it's hard to see the details, so let me just say what the take-home messages are. The vertical axes in both sides of the slide are estimates of annual average ambient PM 2.5, in this case in Delhi. In the next slide, it's going to be Calcutta. And the important thing is not just the sectors that this is coming from, but it's where it's coming from. So the point here is in Delhi, the total bar here, I will go away from the podium, sorry, but the total bar on the right, adds up to over 90 micrograms annual average PM 2.5. The bar just to the left of that is showing you, excuse me, showing you how much of that is coming from New Delhi itself. So maybe 20 micrograms, okay, or a little more than 20 micrograms. But all the other components of the 90 are coming from other states, other countries, natural sources. Again, you can't really see the detail here, but if you're interested, you can look at the slides and actually see the detail. But the important thing is that pollution control has to occur outside the level of cities. Very little is actually being generated within New Delhi itself. The other graph says something about primary versus secondary particles. We've been talking about PM 2.5. Some of it is directly emitted when biomass is burned or coal is burned. But a lot of it comes from what is called secondary particles, which are created when you emit sulfur dioxide from a power plant, nitrogen oxides from motor vehicles or power plants. Those gases actually combine in the atmosphere with ammonia and other substances, and they form secondary particles. And it's important to realize this so you don't just think, well, we're going to control resuspended road dust. So the light bar here, which is supposed to look silver, is actually the fraction of the PM 2.5 in Delhi that represents these secondary particles. You really do need to worry about them. You can't just look at what's being directly emitted as fine particles. I'm not going to go over the next slide in detail. It happens to show the same results for Calcutta, which has a different mix of sources, but this basic point that, of all of the PM in Calcutta, which again is over 90 micrograms, you're getting, in the case of Calcutta, perhaps 25 of those micrograms generated within the city and the rest from outside. Okay, so the implications here are clear. You need to know what the most important sources of air pollution are affecting a city, a district, or a state. You need to know where they're coming from, and you have to really control them at the appropriate level of government to minimize leakage effects, spillovers. You need to look at cost-effective methods of control, and that's going to lead us to look at what are cost-effective methods of controlling pollution from the power sector. Okay, so as I said, this is the results here are coming from a series of papers with Sharath Gadakunda, Pooja Jawahar, Yongjin Park, and actually many other co-authors. Oops, sorry. Okay. So to restate perhaps the obvious to this audience, power plants in India are a major source of greenhouse gas emissions. In fact, in 2015, about a third of greenhouse gas emissions came from coal-fired electricity generation. We've seen the impact on local air quality when we looked at the source apportionment results a couple of slides ago. Okay, in 2018, there were a little over 200 gigawatts of installed capacity, coal-fired installed capacity, with about 95 gigawatts in the planning stages when we did this study in the fall of 2019. Okay, so our main questions are the ones bolded at the bottom of the screen. Now, what would be the benefits in terms of avoided CO2 emissions and reduced PM 2.5 mortality from not building the planned plants, the ones that are on the draft board that would increase capacity by 50%. The second question is, forget for the moment greenhouse gas issues. Should pollution controls be installed on coal-fired power plants to reduce local air pollution? Do they pass the benefit cost test? Okay, so I'll first discuss results from an article that came out in the Proceedings of the National Academy of Sciences in 2021. What we did there was to model the impacts of current, meaning 2018, and planned plants on ambient PM 2.5. We also looked at implications for carbon dioxide emissions. So Pooja and Sharath constructed emission factors for each plant operating in 2018 and in the planning stages in 2019. They added them to a baseline emissions inventory, and ambient PM 2.5 was modeled at a 1/4 of a degree by 1/4 of a degree resolution. Okay, to do the health effects, we did them the same way that we have calculated the health effects. The health effects have been calculated, I should say, in other parts of the presentation, that is using dose response functions from the global burden of disease. And so we will show you results in terms of premature mortality and also CO2 emissions that could be avoided by not building these planned plants. Okay, so our mean estimate of deaths associated with the stock of plants in 2018 was 78,000 deaths. Okay, you can compare that to the 7,444,000 total ambient deaths. Not building these planned plants would reduce annual CO2 emissions by about 500 million tons, and at least initially, when the plants first open, would save about 19,000 lives a year. We'll talk about how that was calculated in a minute. If each plant operated for 40 years, over the lifetime of the plants, you'd be saving something like 840,000 to 1.5 million lives. We'll talk about exactly where those numbers come from. But 70% of the deaths associated with both the existing plants and the new ones could be avoided by installing pollution controls to both reduce sulfur dioxide, selective catalytic reduction to reduce NOx. And our research does suggest that, at least in much of India, these controls pass the benefit cost test. Okay, I won't go into the electricity sector overview. What I'm going to do is to show you maps, which I hope once again come out okay on the screen. The map on the left is showing the location of coal-fired capacity in 2018. The dots represent the location of plants, with bigger dots being greater installed capacity. A lot of dots are on top of each other. So we also showed with color the states with the largest installed capacity. So the state with the largest capacity, which is in pink, is Maharashtra. And the states with the next largest amounts, again, the buckets here are hard to see, but are Chhattisgarh and Uttar Pradesh. Again, it's the bluish and greenish colors that suggest there's not that much installed capacity. So what would be planned and added to what's on the left-hand side? Okay, that's on the right-hand map. So the dots on the right-hand map are additional plants, okay? So a lot of them are or have been planned for the east coast of India, also more in the Chhattisgarh, Jharkhand area. And with these planned plants, you would have installed capacity equal to what was in Maharashtra in 2018 in all of the pink states. So Tamil Nadu, Maharashtra, Madhya Pradesh, Chhattisgarh, Odisha, and you can see them. I think they actually came out pretty well in this case. But there's also increasing capacity up in this northeast corner. Okay, so the question is, what are the impacts of these plants? So again, I'm sorry that the colors don't seem as good as they do on my screen, but darker is more particulate matter coming from coal-fired power plants. The areas that are affected are just affected more. These are actually fairly wide brackets here in terms of the number of grams of particulate matter that are being produced by the plants. You might ask, why isn't there a lot of increased PM in Tamil Nadu? And that's because a lot of these plants are actually, the emissions are being blown into the water. So they're actually very well situated. Anyhow, if you follow or you focus on just the last two bullets here, estimating deaths attributable to the 2018 stock of power plants, they come out to be 78,000. The deaths attributable to the 2018 plants plus the planned plants go up to 112,000. So an increase of 34,000. We're not going to go over these slides, sorry. But now we come to the difference between attributable fractions and avoidable fractions, or how do you evaluate policies when you have these concave dose response functions. So the correct way to do this really is to say, look, if we actually wound up with this stock of 300 gigawatts of installed capacity, and we decided to chop off the last 95 gigawatts, we really want to treat not building the planned plants as a marginal decision from the world in which we have the new plants plus the old plants, okay? And if we do that, given that concave function that you saw many slides ago, the avoidable deaths are going to be much smaller than the attributable deaths just due to the concavity of the function. So even though 34,000 deaths are attributable to the plants, that's treating plants as the average source of exposure. If you do think of at the margin removing them, there will be 19,000 deaths avoidable by not building planned plants. But over 40 years, what we would avoid by not building them is going to grow, the deaths at least, avoided would grow because you have population growth occurring. And you also have reductions in half exposure in the states where these plants are being built. So that's going to move you on the steeper part of the dose response function and will account for more deaths being avoided. Okay, so there are actually two interesting things about the deaths that are being avoided if you don't build these plants. First of all, remember these are much larger grid squares. They're 6 times bigger than we saw before. So the deaths avoided per grid square over 40 years, going to go up to 40,000. So they're much, larger numbers. In terms of where you're avoiding a lot of these deaths, they are, in the Indo-Gangetic Plain, but then going down the eastern coast of India. 49%, almost half the deaths avoided are in Uttar Pradesh, Bihar, West Bengal, which you can see here. But the interesting thing is which way the wind blows. So only 10 gigawatts of increased capacity are in Bengal, West Bengal and Bihar. But they are downwind from areas where you have big increases in installed capacity. And so they suffer, but they're not where the power plants are located. So states with 50% of the planned expansion account for only 20% of the deaths. So which way the wind blows when you're analyzing these policies is very important. Okay, so this is just restating what we've gone over. The last bullet, though, is what I'd like to focus on. We're going to have existing plants continuing to operate, new ones may be built. How can we reduce local air pollution from power plants? So all of the estimates you've seen so far assume that coal-fired power plants are using the pollution control equipment that is actually on them. Okay. There were laws issued in 2015 that really effectively required huge emission reductions at coal-fired power plants, but they haven't been implemented, I guess would be the nice way of saying it. So as we said before, if you actually retrofitted the plants, existing plants that don't have them, which is most plants, with flue gas desulfurization units, scrubbers to take out the SO2, and selective catalytic reduction to reduce NOx, you could reduce 70% of emissions. Okay, in two of our papers, we look at the costs and benefits of retrofitting plants with flue gas desulfurization units, which are, the size of buildings, they're major capital equipment. We looked first at the costs and benefits of retrofitting all coal-fired power plants that were operating in fiscal 2008. And then what we did in the next paper was to put a model plant in 8 locations in India and calculate benefit cost ratios for retrofitting the plant with a scrubber. Okay. So the analysis here is very similar to what we've described for all of the other results. I'm trying to see how many minutes I have left here. We are doing a plant-by-plant analysis, looking at the plant with and without the scrubber. We're looking at the effect of the scrubber on ambient concentrations, in principle throughout India, the impact of that change on mortality. We do it over the life of the 20-year equipment, look at the costs of installing and operating the equipment for 20 years, compare the present value of costs and benefits. Here we are valuing mortality benefits using the value per statistical life, which I hope people are familiar with, because you could give a lecture on that. So the definition is it's the sum of what people would pay for small reductions in the probability of dying that together would sum to one statistical life. And the question is what this should be for India, but let's first look at the impact of retrofitting all 72 plants back in 2008 with a scrubber. The lives you save are small because there's these 72 plants only add up to about 68 gigawatts of gigawatts of installed capacity. The average cost per life saved is these are all annualized values, is $131 US. So if the value of a statistical life is greater than this, then on average, scrubbing passes the benefit cost test, the retrofitting of scrubbers. If you went to the 30 plants, though, with the lowest cost per life saved, so they're in densely populated areas and areas where it's cheaper to install the scrubber, you'd save fewer lives, but still over 9,000, but the cost per life saved goes down to half, okay? So this is, we would say, more cost effective. If you went to the plants with the most deaths, it helps compared to retrofitting all of them in terms of going to the largest plants, which is often the approach, that would actually raise the cost per life saved to $150,000. So the question here, lurking here, is what should be the value per statistical life used in a benefit cost analysis for India? Somanathan and Chakraborty, should say Chakraborty and Somanathan, in a paper that's just come out in World Development Policy, recommended a value of statistical life that's 82 times per capita income, which if you take per capita income for 2013, because that's the year's dollars that we're looking at, would give you about 100, this is per capita income at market exchange rates, it would give you about $125,000 for the VSL in 2013. There is a Gates Commission report on how to conduct a benefit cost analysis appropriately in developing countries, co-authored by Jim Hammett and Lisa Robinson, that recommends a VSL of 100 times per capita income, which would give you for 2013 $152,000. So the 131 is sort of in the ballpark of passing the benefit cost test. But the point is, this varies by plant. Okay, so what we did in the second paper, again, the colors here aren't the greatest. The background here is a map showing population density in India, and the dots are the locations, 8 locations where in fact there actually have been power plants. Dadri, Bunchahar, Bakraswar, Talcher, Karadi, Dahanu, Rayalaseema, and Tuticorin. And we chose different locations because the cost of scrubbing is different in different locations, whether you're on the sea or not. And the number of people exposed clearly varies with population density. Oops. So what we did was to calculate a benefit cost ratio for retrofitting the model plants at each of these locations. We use 3 discount rates. We'll use more in the paper, but what you're seeing on the screen is 3 discount rates and 2 possible VSLs. This is all 2015 dollars that everything was done in this paper. So the 160,000 is 100 times per capita GDP at market exchange rates. The 256 is actually 160 times, it's very high. But to see the sensitivity of the results. And so, regardless of the VSL or the discount rate, you're getting these plants in the Indo-Gangetic Plain passing the benefit cost test with high benefit cost ratios. The Dahanu, Talcher, and Karadi plants are also passing the benefit cost test, and all the 3 cases shown here. The plants in the south, which are not in this very densely populated areas, don't pass the benefit cost test. The ratio is less than 1. But this is mortality only. It's not looking at morbidity. It's not looking at other impacts, such as impacts on agriculture or ecosystems. Okay, so I'm trying to wrap up here soon. Especially in North and Central India, retrofitting power plants with FGDs does pass the benefit cost test. If you put them on a new plant, the costs of installation would go down by about 30% because it's cheaper to build them anew than to retrofit. As I said a minute ago, this is not taking into account morbidity benefits, which added 30% of benefits to what we had calculated back in the information on lost output. No impacts on crop yields, which have been studied, and ecosystems. There actually is a Dahanu plant. The Dahanu plant has actually been scrubbed for ecological reasons, which was actually ordered by judges. So, as I say, the benefit cost ratios should be looked at as underestimates, but they do give you some idea of where to prioritize your investments. So we have answered pretty much all the 5 questions, which I won't repeat. I will hope to be over in an hour, so I hope that's okay for everybody. We've answered these questions, and I guess the question is, what haven't we answered if we really wanted to go farther beyond just simply looking at the health benefits of reducing air pollution in India? So, and this is my last slide, I promise. We haven't really looked, except for power plants, at the costs of different methods of air pollution control. We also haven't looked at what are the most cost-effective methods if we wanted to reduce transport emissions in Delhi. What is the most cost-effective way of doing that? We haven't looked at that. We haven't really looked at the most politically acceptable methods of controlling different sources of air pollution, which is very important. There have been pilot pollution trading schemes implemented by Michael Greenstone and company in the state of Gujarat for PM 2.5 and now for CO2. What really are the politically acceptable methods? And these really have to be answered before you can proceed to really start constructing cost-effective air pollution control strategies. So I will stop here. I've talked long enough, so I will just stop and then answer